Okay, let's unpack this. We are diving deep into the architecture and concepts behind diffusion transformers with representation autoencoders, RAE, DIT. The mission today is pretty precise. We want to give you a professional, comprehensive overview of the research paper. It details how this new methodology fundamentally redefines the latent space for modern generative models. We'll focus purely on the concepts, the empirical results, and the implications. For the last few years, the progress in latent generative modeling, especially with diffusion transformers, DITs, has been, well, undeniable. But the source material we're looking at highlights a critical point of friction, the autoencoder component, the bit that translates pixels to a latent space. It's become a serious bottleneck.
That's really the heart of the problem. DITs are frankly running on legacy infrastructure. They rely heavily on standard VAEs, usually variants of the stable diffusion VAE, the SDVAE. And if you really dig into that architecture, it compromises simplicity. It's built on an older, computationally heavy convolutional design, and maybe more importantly, it focuses on heavy channel-wise compression. This results in those very low-dimensional latents. Think mapping a standard 256 by 256 image down to, what, a 32 by 32 by 4 space.
Right, and limiting the information capacity is only part of the story, isn't it?
Exactly. The other major limitation is the quality of the representation itself. Because those VAEs, they're trained exclusively on a reconstruction objective. So the resulting latent space, it just lacks strong global semantic structure. It captures appearance okay for reconstruction, but it isn't inherently semantically rich. This forces the later diffusion steps to work much harder to generate coherent content. You end up with this cutting-edge transformer backbone, the DIT, operating on a surprisingly weak foundation.
So if the problem is this legacy kind of weak VAE, the proposed solution is a fundamental rethink of that front end. Representation Autoencoders, or RAEs. And this shifts the focus entirely, doesn't it? Away from compression and much more towards representation.
What's really fascinating here is just how elegant the solution is. RAE replaces the VAE encoder with a frozen, pretrained representation encoder. We're talking about powerful modern models, things like DINO v2, SigLIP, maybe MAE. Models already optimized for rich, high-level semantic understanding. This frozen encoder is then paired with a newly trained VIT decoder, a vision transformer decoder.
Okay, so the immediate goal of combining these isn't just efficient reconstruction, it's more like guaranteeing a high-quality latent space right from the start.
Precisely. By freezing a powerful semantic encoder, you essentially get a shortcut. You immediately inherit a semantically rich, structurally coherent, and, importantly, diffusion-friendly latent space. This approach also neatly sidesteps the need for complex multi-stage alignment processes. Methods like RBA, which try to force a weak VAE latent space to align with external semantic encoders after training. With RAE, the latent space alignment is just inherent, built in from the start.
And the paper's overall thesis is, well, it's huge. They're not just saying RAE is an alternative. The authors claim it should be the new default. They argue it demonstrates clear advantages in efficiency, convergence speed, and the final generative quality. Let's start with the architectural comparison then, because the efficiency arguments for RAE seem immediate and pretty dramatic. When we look at the standard SDVAE, the source material notes its design is computationally inefficient, right? That heavy channel-wise compression.
We can put specific numbers on this, yeah. And the scale of the efficiency gap is truly astounding. We're talking performance on a single 256 by 256 image here. The legacy SDVAE encoder, it needs approximately 135 GFLOPs. Its partner decoder needs about 106 GFLOPs. Now, contrast that with an RAE using, say, the DINO V2B encoder. The RAE encoder demands only 22 GFLOPs.
Wait, hang on. 22 GFLOPs versus 135. That's almost a six-fold efficiency improvement just on the encoding step.
It is. And this efficiency gain on the encoder side, the part you run once on your entire massive training dataset, that's hugely important for large-scale pre-training. Even though the RAE produces a significantly higher dimensional latent space, think 768 dimensions per token versus the VAE's 4, the RAE approach is fundamentally more hardware efficient for encoding. Now, the RAE decoder is admittedly more complex. It needs about 768 GFLOPs to handle that higher dimensional input. But the total compute for the autoencoder, encoder plus decoder, is still competitive. And crucially, that encoding step, which determines the latent quality, drastically cheaper.
Okay, but using a frozen semantic encoder and generating this high-dimensional latent space, that really flies in the face of what we thought we knew about latent generative modeling. What was the established wisdom that the RAE approach is actively challenging here?
Right, the prevailing belief system was kind of anchored in two major assumptions. First, researchers often assume that semantic encoders, the ones optimized for high-level features for tasks like classification or self-supervision, they inherently sacrifice the fine pixel-level detail needed for faithful reconstruction. There was this belief, that you couldn't really have both semantic richness and pixel fidelity. One came at the cost of the other. Second, and just as important, it was a generally accepted heuristic that diffusion models performed poorly or were unstable when operating in high-dimensional latent spaces. The whole point of that VAE compression was supposed to be finding a low-dimensional manifold where diffusion could work efficiently. This paper challenges both those points head-on.
So how did the RAE architecture actually achieve that reconstruction quality while still keeping the frozen representation structure?
Well, the RAE design is based on decoupling representation from reconstruction. You start with a robust, frozen, pre-trained encoder, let's call it EAR, say DINO V2B, maybe configured with a patch size Pelo 14 and in a hidden size dollar of 768 toters. For a 256 squared input, this outputs 102 $565 tokens, each 768 dimensions wide. Since the encoder it is frozen, its weights are fixed. It preserves all that semantic knowledge. The only learnable component is the VIT decoder, the $dollars, and that decoder is trained specifically to map those fixed D-dimensional tokens back to the pixel space.
And how is that decoder trained to make sure the quality is there?
It's trained using the standard toolkit, pretty much, the multi-objective reconstruction methods common in VA training. So a combination of L1 loss for raw pixel difference, LPIPS, that perceptual loss component, and adversarial losses, call it math count. The crucial difference here is that these losses are applied to the reconstruction derived from this highly structured, fixed latent space, not some compressed, floating VAE bottleneck. The decoder basically just learns to translate the high-quality semantic blueprint into a visual output.
Let's turn to the empirical results then, the ones that directly debunk that first assumption that semantic encoders can't reconstruct faithfully. The reconstruction FID, or RFID, results in Table 1 seem pretty definitive. The legacy SDVAE gets a 0.62 RFID. That's the baseline to beat.
Exactly. And compare that 0.62 baseline with the RAE results. RAEs using various frozen encoders consistently outperform it. For instance, using MAEB, which is pre-trained specifically through mask reconstruction, achieves a spectacular 0.16 RFID. Really low. Even DINO V2B, which is optimized more for self-supervised structural understanding, still achieves 0.49 RFID. Okay, that's a bit less impressive than MAEB, but it fundamentally and clearly beats the VAE baseline. It demonstrates that rich semantics and high-fidelity reconstruction are not mutually exclusive.
What about scalability within the RAE architecture itself? Does using a much larger DINO V2 encoder like DINO V2L necessarily lead to better reconstruction, or does the decoder capacity become the limiting factor?
That's a good question. The analysis showed that the RFID remained remarkably stable across DINO V2, S, B, and L sizes: small, base, large. This suggests that even the smaller encoders retain enough of that low-level texture information for the decoder to work effectively. However, decoder capacity does matter significantly. A VITB decoder, which is still, 14 times more efficient in GFLPs than the SDVAE decoder, achieves a 0.58 RFID, already better than the SDVAE. But scaling up to the VITXL decoder pushes the RFID down further to 0.49. So you see clear, measurable improvement by increasing the decoder's power. But the point is, even the smaller decoder setup is highly competitive and vastly more efficient than the VAE baseline.
Okay, but the ultimate point of using these modern encoders is the representation strength, right?
Yeah.
This is where the gap between RAE and VAE becomes, completely unbridgeable.
Absolutely. The difference in latent quality is just staggering. Because the RAE encoder is frozen, it inherits the full semantic strength of its pre-training. When you measure this using linear probing on ImageNet top 1 accuracy, a standard metric for representation quality DINO V2B achieves 84.5% accuracy. SigLIP2B is at 79.1%. Meanwhile, the standard SDVAE encoder, optimized only for reconstruction, it manages a, frankly, dismal 8.0% accuracy, just 8%. This huge difference means the latent space that RAE provides is already deeply structured and semantically meaningful. It offers the diffusion model a much, much better starting point. This is the new rich foundation we're talking about.
So, okay, we've established RAE as this superior, efficient, and semantically rich latent foundation. Sounds great. Given all that praise, a researcher's first question has to be, why did the initial attempt to just train a standard DIT on these RAE latents fail so spectacularly?
That's the critical pivot point in the paper, yeah. Despite all of RAE's strengths, the initial finding was that a standard DIT just fails, or underperforms dramatically, when trained directly on these high-dimensional RAE latents. Table 2 in the paper captures this initial failure mode perfectly. When paired with RAU latents, DITs completely fails. It yields a GFID of 215.76, basically. It generates garbage. Even the powerful DITXL model, which performs well on VAE latents, getting around 7.13 GFID, it crashes down to 23.08 GFID when fed RAE latents.
Wow, okay, so that large failure means that simply swapping the autoencoder isn't enough. The fundamental architecture and the training regime of the diffusion model itself, the DIT, has to be rethought to handle this completely different high-dimensional input space.
Exactly. The researchers hypothesized three necessary adjustments to overcome that second piece of conventional wisdom, the idea that diffusion fails in high-dimensional spaces. First, the DIT's architecture itself needed adjustment, specifically for these high-dimensional tokens. Second, the noise scheduling was probably suboptimal. And third, the RAE decoder needed to be robust enough to handle noisy inputs coming from the continuous diffusion process. Tag 2.1 scaling DIT width to match token dimensionality.
Let's start with the architectural hypothesis then. The empirical evidence here, particularly that single-sample overfitting experiment shown in Figure 3, is really fascinating. It gives us a direct view into the model's learning capacity.
It's a very elegant diagnostic tool. They took just one image and measured whether the diffusion model, which is fundamentally a function approximator, could perfectly reproduce that single input after training on it. The observation was striking. Sample quality and, crucially, the training loss only converged down to near zero, meaning perfect reproduction, when the DIT model width, denoted dollars, was scaled to match or exceed the RAE token dimension, no dollars. Since DINO v2b outputs 1 of 168 ITER dimensional tokens, the training only truly converged when the DIT width dollars was set to 768 or higher.
And they made sure to rule out simply increasing model size through depth, right? Which is a common trick in transformer scaling.
Correct. Increasing the DIT depth, for example, doubling the number of layers from 12 to 24, while keeping an insufficient width, say 2D 384 middlers, which is less than 1/87 1 at a middle for 2 meter for 6. This had only marginal effects on convergence. The loss failed to drop sufficiently low, and the generated images remained plagued by heavy artifacts. This strongly suggested that width, not depth, was the critical constraint imposed by this high-dimensional latent space.
Okay, this sounds a bit contradictory, though. If the RAE latent space is so powerful and structured, why does the DIT need such immense width to process it? This forces us back to the theory underpinning the diffusion process itself.
This is where the theoretical justification, which they encapsulate in Theorem 1, becomes essential. The core argument rests on the nature of the flow matching objective, or really just the way diffusion models operate. Injecting Gaussian noise throughout the training process effectively extends the data distribution support. It goes from potentially lying on some low-dimensional data manifold into filling the entire ambient space. It essentially turns it into a full-rank distribution.
Okay, so if the data is diffused and now fills the entire no-dimensional space, you need a function approximator, the DIT, that has sufficient complexity and, crucially, dimension to cover that full space effectively.
Precisely. If the model is too narrow, it simply lacks the effective capacity to capture the signal across all those dimensions. Theorem 1 provides a mathematical lower bound for the training loss, low UT, when you use a function family DT, like a DIT with theta, assuming the full token dimension is 1 array. The minimum achievable loss is lower bounded by the sum of +1 lambda IAT, where those lambdas are the eigenvalues of the covariance of the mixture of the latent representation and the noise, basically the variance in the dimensions the model can't capture.
So for our expert listeners, the practical implication here is profound. If your model with dollars doesn't account for the highest variance dimensions of the diffused data distribution, you have a guaranteed mathematically proven floor on your training loss. You literally can't learn perfectly.
And the researchers demonstrated this beautifully in the simplest toy setting, where the input distribution, PXO, is just a delta function at a single point, $6. In that specific case, the lower bound simplifies really elegantly to just width dealer is less than the dimension. You have a non-zero loss floor. You can't reach zero loss. This theoretical finding perfectly mirrors the empirical observation back in Figure 3. The loss only converged properly when play-day, which makes that theoretical lower bound 0.
Okay, but let's play devil's advocate here for a moment. The initial motivation for RAE was that massive 6-fold efficiency improvement on the VAE encoder. Now, to make the DIT work, you have to make the entire DIT backbone dramatically wider, potentially adding huge computational cost right back in. Isn't that kind of defeating the original purpose?
It's a very fair question, and it highlights a crucial trade-off. What the RAE approach really does is reallocate the computational budget. The efficiency gained on the VAE encoder means we can afford to spend more compute on the diffusion model itself, where the true generative magic happens without necessarily exploding the overall training budget compared to a fully scaled VAE-based DIT. The theoretical necessity of matching width means we have to accept that cost. But as we'll see later with DITDH, they found clever ways to optimize this wider requirement without scaling the quadratic complexity of the entire backbone. ## 2.2 dimension-dependent noise schedule shift.
Moving on to the second fix, the noise schedule. Prior work had already recognized that noise schedules needed adjustment based on spatial resolution, right? Specifically the dollar times the W component. But those models typically dealt with inputs that had a pretty low channel count, maybe 4 or 8 in VAE latents, or just 3 for raw pixels.
Yeah, the problem with RAE is that it introduces this radical shift in the channel dimension, going from maybe 4 all the way up to 768. The crucial realization here is that Gaussian noise is applied across both spatial and, critically, the channel dimensions. When the channel count, the token dimension dollar increases so drastically, the effective resolution per token increases proportionally. This high dimensionality means that the noise, at a fixed level, actually corrupts the information less severely than it would in a cramped, low-dimensional space. There's more room for this signal to survive.
Okay. So the standard noise schedules, which were optimized for low channel inputs, were simply applying too much corruption too fast in the RAE's rich, high-dimensional space. They were basically destroying the signal prematurely.
Exactly. The proposed generalization is that the noise schedule shift must depend on the effective data dimension. That's essentially the product of the token count and the token dimensionality. DMZD more. They adopted the shifting strategy introduced in earlier work by Esser and colleagues. The shifted time step $2 incorporates a dimension-dependent scaling factor, alpha squaring. Here, dollars is the RAE effective dimension, and RS is some defined base dimension, like 4096 in their experiments. This simple modification allows the diffusion model to train much more stably in this high D space.
And the empirical results show just how critical this seemingly small adjustment was.
Massively important. Table 4 shows the huge stabilizing impact. Just implementing this dimension-dependent noise shift dropped the generated FID, the GFID score, their DDTXL model, from that dismal initial failure of 23.08 all the way down to a much more usable 4.81. This is a truly crucial modification. Without it, the high-dimensional RAE space remains unstable and pretty much unusable for effective generation. # 2.3 noise-augmented decoding.
Okay, the third fix addresses a generalization challenge, which is essentially an out-of-distribution, or OD, problem for the decoder. The RAE decoder was initially trained only on clean, discrete latents derived directly from the training data passed through the frozen encoder, but the diffusion process generates noisy, continuous latents.
Right. Think of it this way. The RAE decoder was trained using perfect blueprints, those clean, discrete latents derived right from the training set images via the frozen encoder. The diffusion process, however, is sampling continuously. It generates latents that actually follow a smooth, continuous distribution. Let's call it PNZZ. So when the diffusion model finishes its sampling process, the resulting latent, even if it's close to the target, is continuous and inevitably slightly perturbed by noise. This presents an out-of-distribution challenge to the decoder. The decoder simply hadn't learned how to handle these unavoidable noise components that arise during the generation phase.
So the strategy is basically to intentionally dirty up the decoder's training inputs a bit to make it more robust to noisy inputs later on.
Precisely. They mitigate this OD issue by augmenting the RAE decoder training with additive Gaussian noise, sigma 2i. By training the decoder on this intentionally smooth distribution PNZD, it enhances its generalization capacity for the noisy, continuous outputs generated by the diffusion model. They even introduce some stochasticity by sampling the noise level sigma from a half-normal distribution, aliascum.
This brings us to a pretty fundamental trade-off in generative modeling, doesn't it? Fidelity versus generalization. If you smooth the latent space representation to get better diffusion generalization, you naturally sacrifice some ability to achieve perfect reconstruction fidelity from clean inputs.
And we see this trade-off clearly in the results, Table 5 shows it. This noise augmentation improves the generative quality significantly, dropping the GFID from 4.81 down to 4.28. This proves the decoder is now more robust to the diffusion output. However, it does push the reconstruction fidelity, the RFID, slightly worse. It moves it from 0.49 up to 0.57. This confirms exactly that expected trade-off. The smoothing necessary for generation stability introduces a marginal cost to the decoder's ability to reconstruct fine details from perfectly clean latents.
But the generation benefit clearly outweighs that small reconstruction loss. And we should probably note the strategy has broad applicability too, right? It helped other encoders like MAEB quite dramatically.
Yeah, absolutely. Table 15 shows that for MAEB, the GFID improved dramatically from 16.44 down to 8.38 when this noise augmentation was applied during decoder training. It's generally a useful technique here. So the combination of these three techniques, the width matching, the dimension-dependent noise shift, and this noise-augmented decoding transforms the RAE setup. It goes from that initial failure, remember the 23.08 GFID for DITSL, to a highly efficient and performant framework. By just 80 epochs, the modified RAE DITXL achieves a GFID of 4.28. That's already achieving something like 47 times faster convergence than the VAE-based SciTXL baseline and 16 times faster than alignment methods like RePXL. Really impressive speedup. Okay, so we've established the necessity. The DIT backbone must be wide to handle the RAE's high-dimensional tokens effectively. But as we discussed earlier, scaling the entire DIT backbone width introduces that quadratic growth in FLOPs, which threatens the overall efficiency gain we got from RAE in the first place. This bottleneck seems to have led to the final architectural innovation described in the paper, the diffusion transformer with the DDT head, or DITDH. Yeah, the DITDH is actually an ingenious solution.
Yeah.
It's inspired by the original decoupled diffusion transformer, or DDT. It addresses the scaling issue by decoupling the denoising task itself. Instead of scaling the entire heavy, deep DIT backbone, they maintain a standard-sized DIT model, let's call it $, and then they bolt on a lightweight, shallow, yet very wide transformer head $, which is dedicated specifically to the final denoising prediction.
Okay, so the base model dollar handles the complex, maybe structural context, while the wide head dollar handles the direct denoising output calculation itself.
That's the mechanism, exactly. The standard DIT-based dollars first processes the noisy input $6 and maybe a class label dollar. It outputs an intermediate latent representation, call it ZATT, called MXTTY encoder. Then this wide head dollar takes that intermediate representation, ZEAL, along with the original noisy input and the time step to produce the final velocity prediction, 5-bit T, that bit TGZ2 to 82. The shallow head is primarily responsible for generating that high-dimensional velocity vector without forcing the entire deep backbone to operate at that massive width.
What were the key architectural requirements for this DDT head then? Does wide and shallow have specific parameters they found worked best?
Yes, they did ablations on this, shown in tables 16 and 17. They were very specific. They confirmed that the head absolutely must prioritize width over depth. A 2-layer, 2048 dimensional head consistently outperformed versions that were deeper, like 4-layer, 2048 dim, or narrower, like 6-layer, 1152 dim. And this was true even when the narrow deep versions had similar or even lower FLOP counts. So that 2-layer, 2048 dim head became their default choice. It maximizes the ability to project into the high D space with minimal computational overhead.
And the performance benefit of this DTDH structure, it appears to grow with the complexity of the latent space it receives from the RAE.
Absolutely. The advantage scales directly with the RAE encoder size. When using larger RAEs, like N of 2L, the performance gains were even greater. When they used the maximally wide DDT head, they went up to 2688 dimensions. This really confirms that the head successfully absorbs the increased complexity and dimensionality presented by the larger RAEs. It leverages the quality of the latent space without incurring that quadratic cost penalty in the deep DIT layers.
Okay, looking at the overall FLOP efficiency then, the gains seem pretty substantial. It looks like they realized that original efficiency goal after all.
Definitely. When you look at Figure 6a, the comparison is quite telling. The DIT-DHB model requires only about 40% of the total training FLOPs needed for the standard, full-width DITXL baseline. Yet it still manages to outperform it in generative quality. And the scaled-up DIT-DHXL model achieves an outstanding GFID of 2.16 under a comparable training budget. That's nearly halving the GFID of the vanilla DITXL implementation.
In this combination, RAE's efficient encoder plus DITDH's decoupled scaling, it also translates into record convergence speeds, right?
Yeah, the convergence curves shown in Figures 4 and 6b demonstrate that RADT, and especially RAEDDH, drastically improve upon the state-of-the-art. The DTDHXL's implementation surpasses previous cutting-edge methods like RePXL, MDTD2XL, and SciTXL's very early on in training around the 5x10 GFLOPs mark, which is quite early. Ultimately, RAEDDH requires something like over 40 times less computational budget than some of the VAE-based baselines to achieve its peak performance. This really solidifies RAE as potentially the premier foundation for fast, high-quality diffusion training. So this comprehensive engineering effort, starting from the RAE foundation through the 3 essential training fixes and culminating in the DDTH scaling solution, it all leads to state-of-the-art generative performance.
Let's review the final metrics then. On ImageNet 256 by 256, Table 8 shows the results. DTDH-XL using the DINO V2B RAE achieves a new state-of-the-art FID of 1.51 without guidance. That significantly outperforms all prior published diffusion models at the time, and with auto guidance using the standard Keras et al. Technique, that score drops even further to a phenomenal 1.13 FID.
And this performance scales up very well, too. On ImageNet 52 by 512, Table 7 shows DDH achieving 1.13 FID with guidance after 400 epochs. This effectively surpasses previous strong contenders like EDM2, which was at 1.25 FID, and DDT, which was at 1.28 FID. So clear soda results.
Before we move on from the metrics, it's probably worth pausing just to highlight that technical note they included on the FID calculation protocol. The paper points out a subtle but important detail regarding evaluation standards, which can affect comparisons.
That's right. When you're assessing performance at this level, these really small methodological differences can actually skew comparisons quite a bit. The researchers observed that using class-balanced sampling, that is, sampling exactly 50 images per class for the FID calculation, yields an FID score that is consistently about zero point 0.1 lower, so better, than if you use uniform random sampling across all images. So they actually went back and reevaluated several accessible baselines like CT and RPE, using this class-balanced method to ensure a fair comparison across the board. It just highlights how tight the margins are becoming in SOTA generative research. Hashtag 4.1 efficient high-resolution synthesis.
Okay, one of the persistent challenges for high-resolution generation is always the cost explosion. Doubling image size, say from 256 by 256 to 512 by 512, quadruples the token count, and that dramatically increases the computational complexity during the diffusion process. But the RAE architecture seems to provide a unique efficiency path here, through something called decoder upsampling.
This is a major structural advantage that comes from the RAE's decoupled design, yeah. Since the RAE decoder is trained specifically to map tokens back to pixels, you can obviously decouple the original encoder patch size, PTLRs, from the decoder patch size, PTLR. By setting the decoder patch size PTLRs to be twice the encoder patch size, so PTD equals 2 PTLRs, instead of matching them PTR as PTR, a 512 by 512 image can be reconstructed from the exact same 256 tokens that were used for the 256 by 256 split.
Okay. So this means you can train a diffusion model on the smaller 256 token space, and then reuse that exact optimized model to generate higher resolution 512 by 512 outputs. You completely circumvent the need to retrain or scale the diffusion backbone by 4x in compute.
Exactly. And the results validate this efficiency gain quite nicely. In Table 9, this decoder upsampling strategy achieves a competitive generated FID of 1.61. Compare that to the 1.33 FID achieved by training directly on the full 512 resolution tokens. But crucially, that 1.61 result is achieved with a 4x efficiency gain over what would be required if the token count had been quadrupled. This demonstrates a really vital pathway for efficient, high-resolution image synthesis using these pre-trained diffusion backbones. Hashtag 4.2, the crucial role of RAE's structured representation.
Okay, finally, we need to definitively confirm that the RAE latent space itself is indispensable here. Was the success really due to that combination of high-dimensional structure and semantic richness from RAE? Or could we have just scaled DTDH appropriately on a different foundation and gotten similar results?
The final ablation studies in the paper provide a pretty definitive answer to that. First, they tested DDH on the standard SDVAE latents. If the DDH is wide, shallow head were the only critical factor, we should still see some gains, right? But Table 10 shows the complete opposite. NDTDH XL trained on SDVAE latents actually performs worse, getting an FID of 11.7 than the standard DITXL baseline on VAE latents, which was 7.13. This is pretty conclusive evidence that the DDT head provides little, if any, benefit in low-dimensional, semantically weak spaces. Its efficacy is entirely dependent on the high-dimensional structured input provided by RAE.
Okay, and what about high dimensionality alone? Could we have just used raw pixels but somehow structured them into 768 dimensional tokens to feed the DITDH?
They tested that too in Table 11. And that experiment confirms that high dimensionality alone is entirely insufficient. Training data DDH-XL directly on raw pixels, even when the token dimensionality was perfectly matched to the RAE setting, so 768 dimensional tokens for 256 by 256 images yield terrible results. An FID of 30.56. Compare that to the 2.16 FID for RAE DDH. It's an order of magnitude worse. The conclusion here seems crystal clear.
The success really hinges on that unique combination of the RAE representation and the DITDH architecture.
Precisely. The highly structured, semantically rich representation inherited from the frozen pre-trained encoders in RAE is a necessary precursor. It's non-negotiable. The RAE provides the rich geometry, and then DITDH provides the specific scaling solution needed to leverage that geometry efficiently. Neither high dimensionality alone nor semantic structure in a compressed space is enough to get these results. Hashtag outro.
This has been a truly comprehensive analysis of RAE to DT. We've really detailed how the researchers tackled and overcame critical bottlenecks in latent generative modeling. We started by establishing the limitations of standard VAEs, that old convolutional design, low capacity, weak representations. Then we introduced RAE as the efficient, powerful replacement, leveraging these frozen, state-of-the-art encoders like DINO v2.
Then we dug into the 3 mandatory modifications required to actually tame that high-dimensional RAE latent space for diffusion. That included the theoretical necessity of matching the DIT width to the RAE dimension, the crucial dimension-dependent noise schedule shift, and that noise-augmented decoding strategy to ensure the decoder was robust. And finally, the DIDH structure provided that necessary wide, shallow scaling solution, cleverly circumventing the quadratic compute cost of making the entire backbone wide.
And the resulting system, well, it delivers state-of-the-art image generation performance, achieving 1.51 FID unguided on ImageNet 256, and really revolutionary convergence speed, requiring just a small fraction of the training compute compared to previous methods.
If we try and connect this back to the bigger picture, what this paper fundamentally does is reframe the purpose of autoencoding in generative pipelines. It really transitions the approach away from compression, which has been the historical focus, reducing dimensionality, and moves towards autoencoding as a representation foundation, one that prioritizes semantic coherence, high capacity, and efficiency, especially in that encoding step.
So this raises an important question for you, our listeners, to consider, given the maturity of this RAE approach. The encoder component is now frozen and state-of-the-art. The diffusion backbone is highly optimized via DD-TDH. The decoder remains the only learnable part of the autoencoder. How can we further exploit the structural richness and the high dimensionality of that frozen latent space through improved, perhaps specialized decoder design and training methodologies? What innovations lie ahead for that final pixel translation layer?